for properties of galaxies, we can say that the stellar population of global clusters, like their colors, metallicity, ages, they can somehow track the mass assembly of the galaxies. We see by modalities in colors of global cluster, which reflects the metallicity by modality. Also, we know that galaxies of different masses, they have the global cluster for these galaxies follow different age metallicity relations, which all these can be used to trace this mass assembly for the host galaxy. Also, in another perspective, you can use global clusters to derive the total mass of the galaxy. For instance, you can use a number of global clusters, like the total number of global clusters around the galaxy, or you can just detect these objects around the galaxy and use the dynamics of these objects and somehow as a proxy for mass. Well, this is most important when other methods like stellar kinematics or H1 kinematics fail for some reason. Low surface brightnesses or gas-poor objects they can be a bit tricky. Okay, from now I'm going to talk about finding these objects. So global clusters, let's say they have a typical half-life radius of 3 parsec, which means in different distances, they have different angular sizes. In local group and within few parsecs, you can resolve them from ground-based observations. But then when you go further, for example, in Virgo and Fornax cluster, they are not really resolved from ground. And in the ideal cases, you can resolve them with HST. Further than that, for example, in COMA in 100 megaparsec, they're not even resolved. But then still, you can do things. For example, you can separate them from background objects. So normally global clusters can be found by first a pre-imaging sample selection and do follow-up observations for spectroscopy. And then when you have confirmation, then you have your sample, you can do your science. But it sounds that this procedure is somehow expensive. So there has been always other methods to study global clusters without going through all this trouble. For example, traditionally, it is common to just select them based on optical colors and angular sizes, whether they're resolved or unresolved based on the expected distance. However, one can expect that this kind of works, they also lead to lots of contamination, especially from foreground stars, which I will discuss about it. It can lead to 90% contamination at the end. And some sort of statistical treatment is needed to take into account the uncertainties and derive some numbers for properties of global clusters. So what is important in this case is that when we are dealing with small number of global clusters, like when we look at dwarf galaxies, then large uncertainties are more problematic for sure. Okay, then I'm going to talk about two of the main methods of finding these objects that I've used in my PhD and to study different things. For example, we have color-based selection of global clusters. We use these techniques to find ultra-compact dwarfs in Fornax cluster, which briefly, if I want to describe them, they are, let's say, massive and brighter global clusters. And for historical reason, they are called UCDs. And the majority of them are actually related to global clusters, but some of them are street nuclei of dwarf galaxies. Anyway, we try to look at a Fornax cluster, and in Fornax cluster, 60 of these bright global clusters, or let's say UCDs, are known. You can see they're all inside this purple circle. UCDs are shown with red points here. And when you compare this with the virilis of the cluster, you see that there is a region between these two circles that is empty of these red points. And the reason is that that region is not explored. There have been optical data, and again, with optical data, it is very hard to find this kind of objects. They're not resolved, and colors can be very similar to stars. But what we know is that when we extend our wavelength coverage to near infrared, we can separate them from stars and galaxies. For example, this diagram, red points, again, there are UCDs and global clusters in Fornax. And you can see that the combination of these two colors, optical and near infrared, is quite powerful to separate them from other systems. So that's what we did. We trust this method. We use optical data, which is available, and some near-infrared data from VHS, and some other near-infrared data, which other near-infrared data that we got from ESO archive. Using some machine learning techniques, we put all the information together, train set, and try to identify these sources based on their photometry. And we found these objects at the end. Let's say we found almost 44 highly likely candidates. And just imagine that at first we have like 100,000 of objects. And if our method is a bit uncertain, it can lead just to lots of contamination here. So let's say 1% contamination will give you like 1,000 objects. And because here we have photometry of near infrared, we could explore that what is the fraction of contaminants in optically selected samples, and we see that it can be up to 90% contamination. That's quite significant. So my message from this part is that we can what we did. We can also do the same with Euclid, with near-infrared coverage of Euclid, with the visible part, also with the contribution from other ground-based deep optical survey. It's possible to make this kind of selection based on optical near-infrared colors, which look promising. Then when some other works, they try to go to space, since from ground resolving a global cluster is not really possible, but from space, you can resolve them up to 20 megaparsec, and even I said further than 20 megaparsec, there might be less resolved or even unresolved, but still you can separate them from slightly resolved background galaxies. So this is the ideal case to use HSC, but the problem is that HSC is limited usually to one or few objects. That's, but what I want to say is that even this one observation or few observation can be very, very meaningful for us, and tells us a lot, since selection is very, very clean. So recently we look at this galaxy Dragonfly 44. It's an ultra diffuse galaxy, has been studied before. Ultra diffuse galaxies are like called this ultra diffuse galaxies since Van Dokkum work at 2015, and there were claims about this kind of objects having overmassive dark matter halos similar to Milky Way, but they have a very smaller stellar mass. In particular, for this galaxy, Dragonfly 44, the mass that were estimated by Van Dokkum and collaborators, it was around 10 to 12, like Milky Way, but the stellar mass was 300 less than Milky Way. So this was always a problem. And the main support of this claim, it was actually the number of global clusters around this object. There is studies for stellar kinematics, but they're always uncertain, and you cannot say that much that if this galaxy is overmassive or no. So we look at the data again. I believe that is the picture here is what Van Dokkum had in their work. So you see galaxy in the center, and you see point sources that they've selected. I followed the same procedure, and that's what I get. I try to make it a bit different and follow a bit more careful selection, and that's what I got at the end. So this selection showed me that these objects are actually more compact than what we expect. So global clusters around this galaxy are more compact than global clusters in, let's say, other dwarf galaxies when you compare it with a galaxy's light itself. Then we also continued to count number of global clusters, measured the mass, and we found that, okay, this galaxy is not actually overmass. So again, my message here is that space-based observations just for one object is already gave us a lesson, like these galaxies, they can have a more compact systems of global clusters, something that people start to see actually and notice recently. We're also going to do it more for 6 galaxies, including the Dragonfly 44, again with different data set. And that's what we are doing at the moment. So at this point, I want to say that Euclid has, well, we know that a special resolution comparable to HSC, but it's not limited to few sources now. So Euclid will observe hundreds of thousands of galaxies, UDGs, dwarfs, or bigger galaxies, and it will be incredible data set for us. Okay, so for my conclusion, I bring this part of the Red Book of Euclid about the science that can be done with Euclid, and about global clusters, there's this part that says depth and resolution of Euclid is helpful for identifying these global clusters within 5 megaparsec. And based on what I said here, I want to change it a bit. I want to say that the wavelength coverage is also important. The near infrared is very helpful. And we can also go a bit further to maybe 100 megaparsec, which is mostly limited by the depth of the data and not resolution or other things. So there is one more point here that since I'm talking about global clusters and studying galaxies through their global clusters, we also at first place need some global cluster around that galaxy. So theoretically, we don't expect any global cluster for galaxies lighter than 10 to 9 solar mass. So yeah, that's the limit here at least. Yeah, okay, so thank you. I hope I gave some quite useful information about this subject. And I didn't talk about the science here. It's more about finding these objects, but I believe that there are lots of interesting questions about global cluster itself, about the connection between global cluster and galaxies, and I show some of them here as my favorite ones. Thank you.
Thanks very much. So I had a question on maybe I missed something, but how do you turn the number of globular clusters into an estimate of the mass of the galaxy if you don't have kinematics? I thought you would need some sort of a stellar dynamics virial.
So yeah, so there was a well-known relationship between the total mass of a galaxy and total mass of global clusters. And then later people showed that if you just, so this relationship was found observationally. And then later people also showed that if you just take like an average mass for global clusters, and you can turn that relation to number of global clusters, and it still works. So just number simply can give you an estimate of halo mass.
So you extrapolate.
That's observational, but then also you can. It's also an outcome of hierarchical formation for global clusters of galaxies. More massive galaxies just get more dwarf galaxies, and they just get more global clusters of these dwarf galaxies, and they just the population of global cluster increases.
Right. Any other questions? I don't see any. Okay, then thank you very much.
Okay, I'll stop sharing.
Okay.